Hello and welcome to another Advent of Code video. We're here for day 22. We're getting close to the end now, but this one I felt wasn't that difficult. It was a lot of reading, but it wasn't that difficult. Anyway, let's jump into it and I'll explain how this problem goes. Oh, I forgot to open up the thing. Whoops. Here we go. So the problem that we have for day 22 is we're playing a card game where there are two players' decks. And this is in the wrong directory too. Man, I really didn't prep for this properly. Oh, it's my home directory. Oh, sorry about this. Temp AOC. All right, let's open up the parsing so you can see what it looks like. So the input is two decks, and the players are going to play against each other in a game. And if you've played the card game War, this looks very similar to that. However, in this card game, there are no duplicate numbers, so we don't have to worry about the complicated rules of War. However, Part 2 will have its own set of complicated rules, so we don't quite get out of that. But yeah, the parsing we're going to do first. Note that I'm going to represent each of the players as a deck type in Python. Deck is a double-ended queue, and it exists in the collections module. And we're going to use a deck because it's going to make it really easy to simulate a DECK deck, in that you draw from the top and you put things on the bottom, and so it's a unidirectional queue. And yeah, this represents a double-ended queue class. We don't actually care about pushing in the other direction, but this is still efficient for what we want to implement. You could use a list, however, popping from the front of a list is going to incur a bunch of overhead. You could build your own circular buffer that has, your pointers to where the start and the end is, and you shift it around circularly so you don't incur more allocations, but Deck does this for us, so we don't have to really think about it. I don't exactly remember how it's implemented. I think it's implemented as a resizable circular buffer, but I don't know. I would have to read the source again. Anyway, so we're going to represent these two as decks. Parsing this input is pretty straightforward. Let's do player 1s and player 2s equals s dot split on blank line. That way we get different parts here. And we have, let's see, player 1n equals, I guess we can just do player 1 equals collections dot deck. And we're going to initialize that with a comprehension. Int line for line in player 1s dot split lines 1:. That way we chop off this first line here, but otherwise we make an integer for each line. And player 2 is basically the same, except we replace the 1 with a 2 and return player 1, player 2. So that should do the parsing. And cool, yeah, we get two decks out here, so you can see we get 92631 and 584710. Cool. So that's part 1, or that's the parsing. Let's go to part 1, part1.py. And for part 1, the card game is played similar to War, and in this case, the high card wins for each individual round. And the winning player will put the winning card on top and the losing card on the bottom of their deck. And so, it'll play back and forth like that. And at the end, we need to compute the deck checksum, which is multiplying the position from the bottom multiplied by the card's value and all the way up through the deck. And so this will give you some unique number at the end. But let's implement this. Let's see. I am going to do while player 1 and player 2. So while we have, both of the players are in the game, they haven't decked out yet. We will retrieve two cards from both of them. So we'll do card 1, card 2 equals player 1 dot pop left. So I'm going to represent the left-hand side as the top of the deck, and this is the bottom of the deck. Player 2 dot pop left. And so we can say if C1 is greater than C2. So if player 1 drew the larger card, then we can do player 1 dot extend C1, C2. So this was the winning card, and this was the losing card. Otherwise, player 2 won, player 2 dot extend, and the winning card followed by the losing card. So that's basically the logic for playing the game. So if we put a breakpoint here, and we run this, we can see player 1 lost and player 2 won the game. We need to figure out which player won and then do that deck checksum thing here. So let's see, if player 1, winner equals player 1. Player 1, otherwise winner equals player 2. And we need to compute the sum of all of those things, so total equals 0. I'm going to use a cool trick to reversed and enumerate to get these pieces out here. So you can do reversed of player 2, and that will give you a deck reverse iterator. Print list of this. You can see that's it in reversed. And then we can use enumerate over this. However, enumerate's going to be off by 1. Our indices are going to be starting at 0, but you can tell enumerate where to start, and so then we can get these pairs to do the multiplication out. So we can do for I n in enumerate reversed winner, because it comes from the bottom, total plus equals I times n, and then return total. And so if we do that now, player 3, or Python 3 part 1, why do I get the wrong value? Wait, did I do this wrong? C1 is greater than C2. Player 2, C2, C1. That looks right. Let me compare my actual solution since it looks right. Okay, so this is where I did my parsing. I used N1, N2. N1, N2, N2, N1. Yeah, that looks right. Oh, I forgot to do enumerate by 1. Whoops. That would do it. Okay, there we go. Now we get 306, what we expect for part 1. Okay, so that's part 1. Part 2 gets a lot more complicated. I found it really difficult to read, so I tried to summarize all of the rules here. So let's copy part 1 to part 2.py. Well, I guess we could talk about the algorithm efficiency here. And it's actually kind of undeterminable, the algorithmic efficiency, because you know, this loop could run forever in theory. It doesn't in practice, but I think it could run forever. But it's probably somewhere in the order of around n squared. But you know, you can't really know because this loop could be forever. Anyway, let's look at part 2. Part 2.py. So we have a different setup for part 2 here. In part 2, if any player has no cards, the other player wins. But the thing here is we're playing Recursive Combat. So I made a separate function to do the recursive the recursive part of this, and I called this, I don't know, compute helper. And compute helper is going to take player 1, which is a deck of int, and player 2, which is a deck of int. And it's going to return 2 things. We need to know who won and what their winning things are. So we have a tuple of... I just used bool to represent did player 1 win. You could probably do something more clever with like enumerations, but this was good enough for me. And a deck of ints for the winning deck. And this is where we'll actually implement all of this logic here. But before we jump into that, we can just call our compute helper in our compute function to figure out who won and the answer here. We don't care about who won. We just want to know the winner, and that's equal to compute helper player 1 player 2, and this will play out our recursive game. We don't have to change this code at all because it's still the same here. Okay, so let's do our recursive combat. I decided to do this as an infinite loop. But, you know, you could do this with all of the termination conditions here. But this, I felt, was the easiest. If any player has no cards, the other player wins the game. Okay, so we can start by doing, if not player 1, then return false and player 2. If not player 2, return true and player 1. So this will handle that first bullet point. Second bullet point, if the current game state has been seen before in that game, player 1 wins. So whenever I hear something like this, I'm thinking a set of all of the states. My implementation of this was actually not super efficient. There's probably a better way to represent the game state, but I just made a scene set here and checked this scene set and saw if we had this state in it already. And so what I did is I made and this is the inefficient part. I made game state equal to a tuple that contains the tuple of player 1 and the tuple of player 2. And the reason this is inefficient is this creates a full copy of these decks over and over and over every time this loop runs. And that's pretty slow. It's basically doing a, ON over each deck every single time. But then I said if game state in scene, and so let's see, if the current game state has been seen before in that game, player 1 wins. So we would say return true and player 1. So that's kind of, a bit in the advantage of player 1, but it prevents the game from going infinitely. Okay, after that, players draw cards. So let's do that same thing that we did before. C1, C2 equals player 1.pop left and player 2.pop left. Okay, if both players have card counts more than their card's value, a recursive game begins. In a recursive game, a sub-deck is taken from the remaining card count. The decks are unaltered while making a sub-decks. Okay, so if C1 is less than or equal to the length of player 1, and C2 is less than or equal to the length of player 2, so this means that player 2 has more cards left than the value, and player 1 has more cards left than the remaining value, then we're going to play a recursive game of this thing. And this is kind of the tricky part, or in my opinion, like one of the tricks that I did here. We need to create a subdeck based on the length of these values here. And you'll notice something about decks in Python. Import collections, d equals collections.deck. 1, 2, 3, 4, 5. We have a deck here. Decks are not sliceable intentionally because slicing an arbitrary position might be inefficient, and implementing a proper slice is difficult. However, iteration from both sides is still supported. So for x in d, print x, and that allows you to iterate through it. You can also do this in reverse. We don't actually need this for our problem. Reversed. Print x, and you can see that allows you to iterate in reverse. And anytime that I see that we can iterate, this gives me a hint that we can use iSlice, which is an iterable slice, which kind of skirts around this type error here. So if we import itertools and we do itertools, and I don't use itertools very often, so this is kind of a special treat, I guess. If we do itertools.iSlice on deck, and let's say we want the first 3 elements, this is going to give us an iSlice object back, and we can use this to make a new deck. So if we did collections.deck on this iSlice, you can see we get a sub-deck here, and the original deck is left the same. So we're going to use this trick to make our sub-decks. So sub player 1 equals itertools dot, oh my goodness, collections.deck, itertools.iSlice, player 1 and card 1. And we need to import itertools, of course. Import itertools. And then we'll do the same for player 2, but we'll use C2. And then we'll figure out whether whether sub player 1 or sub player 2 want this. So we're going to recursively call our helper here. So player 1 1, and we don't care about the second value, equals, and this is our recursion, compute helper sub player 1 sub player 2. And so again, we'll follow the same sort of thing as we did before. If let's see, if the winner of the subgame takes the cards and put the winning card on top of the losing card. And there's a note here that this doesn't necessarily mean that it's the larger card, it just meant that they won that subgame. So we'll do if player 1 1, then player 1 dot extend C1 C2, otherwise player 2 dot extend C2 C1. So this is similar to what we did before. We still have to implement this last little part, otherwise high card wins, similar to round 1. So otherwise, if C1 is greater than C2, then we'll do player 1 dot extend C1 C2. Otherwise, player 2 dot extend C2 C1. Oh, I also forgot to update game state up here. Game state dot add. Or wait, scene dot add game state. Scene dot add game state. That would have been a fun one to debug. But yeah, so this is going to loop forever. We're going to continually build up this game state to try and figure out whether we get this infinite loop detection or if somebody decks out, and we're returning whether or not player 1 wins. And this implements our recursion here. I think this is the proper implementation. Let's see, Python 3 part 2.py. Tuple is not defined. Okay, forgot an import. 291, which is what we expect for part 2. Cool. And that's how I implemented this. Now, this solution is pretty slow. Let's see, antivirus code, ASC day 22. This was pretty slow for part 2. From my standards, like this takes, you know, 3,700 milliseconds to run, which is kind of slow. And that's probably due to the way that I'm managing game state. I could probably think of a more clever way to implement this, like maybe even use the deck checksum. Although, is that unique? Might be unique. I don't know. I would have to think about it. If it's not unique, I could probably pick a bigger value to multiply by, and then it would be unique. But representing a hash of these decks without actually doing a full memory copy over and over and over, that probably would make this faster. But I don't know. Exercise left to the reader. Anyway, hopefully this was useful. I'll see you again for the next day. Button. Oh, we can just click this then.